Hello, welcome to this clip looking at the interaction between acid-base indicators and electricity. So normally in A-level chemistry we treat acid-base indicators and electrolysis as two separate topics, and they don't really cross over very much, but this clip looks at an example where some of my students created a practical whereby acid-base indicator changes plus electrolysis actually came together in one practical. So we'll look at the background first before we go on to showing you a clip of what actually happened when we did it. So acid-base indicators are essentially weak acids themselves, which partially dissociate into a proton and then the rest of the indicator molecule. To keep things simple, we'll refer to the remainder of the indicator molecule as HIN. So in any partial dissociation, it behaves like a dynamic equilibrium, and as such we say in chemistry that it's governed by Le Chatelier's principle, and this is introduced at GCSE and then developed further at A-level and beyond. So in essence this says that in a chemical equilibrium which is in the process of dynamic equilibrium, the position of equilibrium will shift in the direction which minimizes the effect of any imposed change in conditions. So changing conditions could mean a change in temperature, change in pressure if we're looking at a gaseous mixture, for example, or change in concentration, which would be applied to a liquid, a solution, or maybe a mixture of liquids. So let's take the most common indicator, litmus, as an example. You'll see that I've color-coded my equation. So if we look at the two colors, the undissociated indicator molecule is red, and the dissociated indicator ion is In minus, is blue. So now let's think about how litmus is used. So remembering that litmus turns red in the presence of acids and blue in the presence of alkalis, let's have a think about how Le Chatelier's principle governs what happens. So if we add H+, so the blue indicator ion reacts with incoming H+ to create more red indicator molecules. This minimizes the effect of adding H+ because the excess protons you've just added are used up. So that means blue litmus turns red. So if we add alkali in the form of OH-, the incoming OH- ions react with the H+ on the right-hand side of the equation, which I've now highlighted. So these are removed when they produce a water molecule. And what happens to replace it is that the red indicator molecule on the left-hand side dissociates to form another H+ and an indicator species, an indicator ion. So in terms of Le Chatelier's principle, we have to say something about the shift in the position of equilibrium. So in purple I've added an annotation to say what direction the position of the equilibrium shifts in, because that's an important part of Le Chatelier's principle. You can see that from inside the box. Okay, so now let's have a look at what happened when we used electrolysis to influence this reaction. So another indicator that we often use is called universal indicator. This is actually a mixture of several different indicator compounds, and each one will have separate colour changes at a given pH. So if you look at the little chart we've got here, it shows you that you've got three different indicators that work at three different pH values, and they also give three different colour changes that you can see visibly with the naked eye. So mixing these three together would give you a sort of universal version that could work from pH 3 or pH 2.5, for example, all the way up to pH 10. So universal indicator is a commonly used mixture of indicator compounds just to give us a quick sort of estimate of what the pH of our mixture is that we're working with. So the experiment we did is to set up a Petri dish with some filter paper soaked with saturated sodium chloride solution and also the indicator. About 20 drops of indicator was needed. So we connected up a power pack with a positive terminal connected to the filter paper, and the negative terminal, here is a carbon electrode, which is used to write over the filter paper. So I'll insert a video of what we showed, what we found with the universal indicator, and then you can see for yourself what actually happened. So what's happening here is that where the negative electrode is touching the filter paper, the circuit is completed, current can flow, and the H+ ions are being attracted to this negative electrode, being the opposite charge. So obviously removing H+ from the mixture shifts the equilibrium position to the right, and you can see that I've changed the colour coding to reflect the sort of orange to dark green colour you can see in the demonstration. So in this case it's a different indicator. We're using a single molecule. This time it's bromocresol green, the structure of which is shown on the left of the screen at the bottom. So let's start the video and see what this does. So you can see quite clearly that this draws a sort of blue colour across a green background. So from that you can see quite easily that the indicator itself is green and the indicator ion is actually blue. So the same equilibria considerations would exist here. Removing H+ from the mixture would shift the equilibrium position to the right again, and at the negative electrode the H+ ions are attracted, which has the same effect as removing them from the mixture in the equation above. Okay, so we hope you've enjoyed this video clip, and we enjoyed sharing some of our clips themselves with you. Hopefully it's shown you how two different aspects of chemistry can combine into one, and it also brings in a bit of equilibria, which we've been doing lately in college. Okay, so thanks for listening, and until next time, see you soon.